Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
In space, gravity as we experience it on Earth disappears. Astronauts float freely, liquids form spheres, and even simple movements become difficult to control. Living without gravity is not just unusual, it's physically challenging. Muscles weaken, bones lose density, and the heart struggles to circulate blood properly. For missions lasting months or years, such as trips to Mars or long-term lunar habitats, these effects can become serious health risks. Synthetic gravity refers to creating a force that feels like Earth's gravity, even when there is no nearby massive object. It's not a new type of force, but a way to mimic the effects of gravity on the human body. Engineers and scientists are exploring methods such as rotating spacecraft to produce centrifugal acceleration, linear acceleration through continuous thrust, or experimental magnetic systems. Each approach has distinct advantages, limitations, and health considerations for human in space. I'm Drew, and in this episode, we'll explore how synthetic gravity works, why real gravity is impossible to produce, and how synthetic gravity could make long-term space missions safer and more sustainable. We'll explain the physics behind motion-based artificial gravity, the engineering challenges of building rotating habitats, and the ways this technology could protect astronauts and support life beyond Earth. Understanding synthetic gravity is a crucial step toward turning space from a place we visit into a place we can live. Gravity seems simple at first glance. You drop a pen, it falls. You jump, and you come back down. It's so familiar that most of us never stop to think about what's actually happening. In reality, that ordinary downward pull is one of the most remarkable phenomena in the universe. When Isaac Newton first described gravity in the late 1600s, he didn't know why it existed, only that it worked. His insight was that gravity wasn't unique to Earth, it was universal. Every object with mass attracts every other object, no matter how far apart they are. You're pulling on the moon right now, just a very, very, very small amount. The same law applies to why apples fall from trees and why the planet orbits the sun. Newton showed that the strength of gravity depends on two things: the masses of the objects and the distance between them. The further apart two objects are, the weaker the pull. Specifically, it weakens with the square of the distance. If you move twice as far from something, its gravitational pull becomes 4 times weaker. That's why the moon's gravity is so gentle compared to Earth's. It only has about 1/6 of Earth's gravitational strength. If you weigh 150 pounds on Earth, you'd only weigh 25 on the moon, and you could jump 6 times higher with the exact same effort. This relationship, known as the inverse square law, is one of the most elegant equations in physics. It perfectly predicts how planets move and how fast spacecraft must travel to escape Earth gravity. But Newton's model had limits. He could describe gravity, but not explain what caused it. 2 centuries later, Albert Einstein changed everything. He realized that gravity isn't a force pulling objects together. It's the shape of what he called spacetime. He thought of space as not an empty nothingness, but as a flexible fabric that can stretch and curve. When you place something massive, like a planet or a star on that fabric, the fabric bends downward, forming a dimple. Smaller objects, like moons or satellites, move along those curves. They aren't being pulled by a mysterious force. They're simply following the natural paths of curved spacetime. This concept sounds abstract, but a simple analogy helps. Imagine stretching a rubber sheet tight and then placing a heavy bowling ball in the center. The sheet sags, forming a dip. Now roll a marble nearby. It'll spiral inward, not because that ball exerts an invisible tug, but because the surface itself is guiding the marble's motion. That's the concept of how Earth keeps the moon in orbit, and how the sun keeps the Earth circling year after year. Thinking of gravity this way also reveals why creating real gravity from scratch is nearly impossible. To make true gravity, you'd have to warp space-time the same way a planet does, and that takes unimaginable amounts of energy. Even to produce 1% of Earth's gravitational pull over a small area, you need about as much energy as all the world's power plants generate combined, and that would still be far too weak to feel. The conclusion is clear. While bending spacetime is theoretically possible, it's hopelessly impractical with any known technology. That's why scientists and engineers turn to something else entirely: imitation. Instead of trying to recreate real gravity, they focus on mimicking how gravity feels. If you can't bend spacetime, maybe you can use motion and inertia to trick the human body into thinking that there's real gravity there. But before anyone could test ways to fake gravity, we first had to understand what happens when it's gone. On Earth, we can't turn off gravity, but we can simulate short bursts of weightlessness. One of the main ways NASA and other agencies do this is through parabolic flight. Plane climbs steeply, then dives downward in a controlled arc. Inside, everything, passengers, tools, even droplets of water, float freely for about 20 seconds as the aircraft and everything inside it are falling at the exact same rate. The experience is exhilarating, but also disorienting, which is why NASA's training plane earned the nickname the Vomit Comet. Another way to create weightlessness is through drop towers. These are very tall vertical shafts, where small capsules are lifted to the top and then released. During the free fall, the capsule and everything inside experiences true microgravity for a few seconds before being caught at the bottom. Scientists use these brief moments to study how fluids flow, flames burn, or even how living cells behave when gravity no longer dominates their environment. These experiments make one thing clear: gravity isn't just a background feature of life. It's woven into the design of everything our bodies do. It guides how our blood circulates, how our bones bear weight, and how our brains sense up from down. Without it, every system starts to behave differently, often in ways that are dangerous over time. So, if we want to live and work in space for months or even years, we have to find a way to bring gravity with us. We can't warp space-time like a planet, but we can use motion, specifically rotation, to recreate that same feeling. By spinning a spacecraft, we can generate a force that acts just like gravity, pressing astronauts toward the outer walls and giving them back that familiar sense of down. It's not real gravity, but for human biology, it's close enough. And understanding exactly how that illusion works is key to making life beyond Earth sustainable. Weightlessness might look fun in videos from the ISS, but living in it day to day is one of the hardest parts of being an astronaut. Without gravity constantly pulling downward, every system in the human body starts to change in ways we don't experience on Earth. Muscles are the first to weaken. Here on ground, they're always working, even when we just stand still. Our legs are supporting our weight, and our back hold us upright. In orbit, none of that happens. Without gravity, every movement becomes effortless. You can float across a room without a single push. But that convenience comes at a cost. The body assumes it doesn't need strength anymore. Astronauts can lose up to 20% of their muscle mass in just a couple of weeks, especially in the legs and the back. Bones suffer next. On Earth, bones constantly rebuild themselves to handle the pressure of carrying weight. In 0G, that pressure disappears, and the body can start removing calcium from the skeleton. Over about a 6-month mission, astronauts can lose 1 to 2% of their bone density every single month, about 10 times faster than the most severe diseases do on Earth. When they come down home to Earth, it can take years to fully recover that bone density. Even the heart changes. Since it no longer has to fight gravity to pump blood upward, it slowly becomes rounder and less efficient. Fluids inside the body shift upward too, collecting in your chest and head. That's why you can sometimes see astronauts' faces look puffy in photos from space, and why many of them complain about constant nasal congestion. The increase in pressure in the skull can even cause blurry vision, a condition NASA calls spaceflight-associated neuroocular syndrome. Then there's the brain. Gravity gives us a clear sense of orientation. Up, down, left, right. Take that away, and the brain loses one of its most important reference points. At first, astronauts feel dizzy and disoriented. They sometimes report space fog, where it becomes harder to concentrate or judge distances. Even simple tasks like turning a screw or pouring water can feel confusing when there's no down to guide your hands. All of these problems point to one truth. Human biology evolved to depend on gravity. Without it, you start to unravel. That's why creating synthetic gravity isn't just about comfort, it's about survival. Long missions to Mars or beyond will take months or even years, and no amount of exercise alone can fully prevent the damage from 0G. The only real solution is to rebuild gravity itself, or at least something that feels close enough to fool the body into believing it's still home. So, how do we actually make gravity without a planet? The answer, at least for now, isn't through bending space-time or building miniature black holes. It's through motion. Imagine holding a bucket half full of water and spinning it in a vertical circle. Even when the bucket's upside down, the water stays inside. The spinning motion pushes it outward, away from the center of rotation. That outward push isn't a real force. It's the result of the water's momentum wanting to move in a straight line, while the bucket is constantly redirecting it in a circle. The effect feels just like gravity, pressing the water against the bottom. The same idea can apply to people in space. If the spaceship spins fast enough, everything inside would feel a pull toward the outer rim. That pull would act like artificial gravity. Engineers call it centrifugal force, though technically it's an illusion created by inertia. Your body isn't being pulled outward. The floor is pushing inward to keep you from moving in a circle, and you feel that as weight. The strength of the synthetic gravity depends on two things: the radius of the rotation and the rate of spin. Larger stations can spin more slowly and still create the same sensation of gravity, while smaller ones need to rotate faster. On paper, this relationship is simple. The acceleration equals the square of the rotation speed times the radius. But in practice, getting that balance right is one of the hardest parts of these rotating spacecraft. If the radius is too small, the spin rate becomes uncomfortably high. For example, a habitat only 10 meters wide will need to spin around once every 3 seconds to produce the same gravity as we feel on Earth. It's fast enough to make most people sick. The inner ear detects rotation very precisely, and the rapid spinning causes disorientation, nausea, and a strange twisting sensation known as the Coriolis effect. Coriolis effect is what happens when you move within a spinning system. Suppose you're walking around inside that habitat. When you walk in the direction of the spin, the floor seems to push up slightly harder. When you walk against it, you feel lighter. If you toss a ball straight ahead, it curves to the side instead of flying straight. Even pouring a drink becomes odd, because the liquid seems to drift in directions your brain doesn't expect. The faster the rotation, the more intense these effects become. To reduce that discomfort, engineers prefer slower spin rates, no faster than about 2 rotations a minute. That means the habitat must be large. A station with a radius of about 100 meters could spin slowly enough to feel natural while still producing full Earth gravity. That's roughly the size of a sports stadium, which makes construction a major challenge. Early scientists imagined these designs decades ago. In the 50s, Wernher von Braun proposed a huge rotating wheel in space, 76 meters across, with people living along the rim. It would spin once a minute to create comfortable gravity for long missions. NASA revisited the idea in the 60s and 70s, running experiments on small human centrifuges to test how the body handles continuous rotation. More recently, the Japanese space agency JAXA conducted animal studies using small rotating habitats on the ISS to study bone and muscle responses under different artificial gravities. Modern designs often use 2 modules connected by a long cable, spinning around a shared center of mass. The crew lives in one module, while the other acts as a counterweight. This setup is lighter and easier to launch than a full ring, and by adjusting the cable length, engineers can fine-tune the level of gravity. The system could even be stopped or started by changing the rotation with small thrusters. There's also the possibility of partial gravity habitats, structures that don't simulate full Earth gravity, but something between no gravity. Mars, for example, has only 0.38 times the force of gravity of Earth. A rotating spacecraft could create that level of pull with a much smaller radius and slower spin, reducing instruction challenges while still protecting astronaut health. Some researchers even suggest spacecraft with adjustable gravity sections, where crews can move between 0G, lunar G, and Earth's gravity environments for training and experimentation. Walking inside a spinning habitat would be a strange but fascinating experience. Near the outer rim, your feet would feel the pull of gravity. As you walk inward toward the center, the feeling would fade until you begin to float. The direction of down always points outward from the center. So if you looked across the station, you'd see people on the opposite side of the ring walking upside down relative to you. It would take some getting used to, but after a few days, your body and brain would adjust. In the end, spinning remains the most practical path to artificial gravity. It doesn't rely on new physics or exotic materials, just precise engineering and careful control of motion. The challenge isn't whether it works, but how to build it safely, comfortably, and affordably at the massive scale needed for long-term space missions. Looking ahead, synthetic gravity is no longer just science fiction. It's becoming a priority for companies and space agencies looking to support life in orbit, long missions to Mars, and even space tourism. One of the leading players is Vast Space, founded in 2021. They plan to launch their first commercial space station, Haven 1, around 2030, with long-term goals of creating space stations capable of artificial gravity. Their vision includes stations where rotation or motion gives a gravity-like effect to support human health and operations. Another company, the Orbital Assembly Corporation, is designing the Voyager station, which aims to use rotating habitat modules to provide near-lunar gravity. The plan includes the truss construction in orbit and a scaled prototype on Earth to test structural components before full deployment. There are also shorter duration, more specific experiments in progress. Blue Origin recently spun a capsule 11 times a minute to mimic lunar gravity for experiments. These flights test hardware and techniques in realistic partial gravity environments. NASA is running ground-based studies as well. One example, a short-radius centrifuge experiment lasting 41 days to use daily rotation to counteract effects of bed rest on human subjects. The results show improvement in cardiovascular and muscular health when artificial gravity loading is applied comparatively to zero-gravity controls. These developments show synthetic gravity is moving from theory to prototyping. Stations with rotating modules, capsules able to simulate lunar or Mars gravity, and medical experiments validating biological protection are already being built or tested. Within 1 or 2 decades, synthetic gravity could be essential for deep space missions, orbital habitats, and making long-term human life in space safe and livable. Gravity is no longer something we take for granted. It's a condition that we can engineer, shape, and bring with us beyond Earth. From the spinning habitats of von Braun's early designs to the modern prototypes being developed by Vast Space and other pioneers, the pursuit of synthetic gravity demonstrates that humans are capable of adapting our environment to meet our biological needs. By understanding how motion, rotation, and inertia can mimic the pull of a planet, we can safeguard the health of astronauts on long missions, make laboratories in orbit more productive, and even design the first floating cities or space hotels. The science behind synthetic gravity is precise and rigorous, but its impact is profoundly human. It restores orientation, preserves strength and bone density, and allows life to continue in a place where our bodies would otherwise deteriorate. It bridges physics, biology, and engineering, showing that even in the emptiness of space, we can recreate conditions that feel like home. If we can carry gravity with us, the next question is what else we might bring. Air, water, ecosystems, even entire environments engineered for human life. Synthetic gravity is just the first step in making space not just a destination, but a place where humans can truly live.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.